Hello, everybody. Let me go on and tell you what we've been doing here on this fundamental problem of the scale of the universe and the expansion rate. And we've been doing something a little bit different than what you've been hearing about. The POP1 ladder that Adam Rees and his team has been pursuing is now pretty familiar to everybody, and it involves three different stages. At the top is measuring supernova and distances at large scales, but they have to be calibrated through cepheids and then with perhaps geometry of parallaxes on small scales. But all of this involves, since it involves cepheids, it involves galaxies with gas in them. So we have been pursuing a separate way of getting this Hubble constant that is completely independent. There's been, of course, controversy between Adam Rees's team and Wendy Friedman's team, which is very familiar. So clearly there's a need for a third way. And we have a third way that is completely independent. So we're using only old stars to get the distances. And so at the top end, it's going to be looking at surface brightness fluctuations in old galaxy populations. And we get the distances to that methodology from tip of the red giant branch, a methodology then that involves old stars. And then that's calibrated geometrically with Gaia parallaxes at the bottom end. So that's an entirely independent methodology, and it's going to be using basically James Webb information. So, tip of the red giant branch. This is a well-known phenomenon. It's been well studied. It's very understood. Then the evolution of stars up the red giant branch, and at the tip of the red giant branch is what we're going to be trying to measure. So, with Hubble Space Telescope, a lot of nearby galaxies have been observed. Essentially everything within 10 megaparsecs has been observed for tip of the red giant branch. And here you just see some examples of galaxies in the local group, and you see that in every case, the red giant branch is well developed and the tip is well defined. So now with JWST, we're starting to do the same thing, and this is one galaxy in the local group that's been observed already. And these are, over here we see other examples that will be observed in the next, in the cycle that's occurring right now. Now, another important part of this story then is we will be using as a 0-point calibration for the present talk, NGC 4258. Now this is a galaxy that has this interesting maser that is given a very precise geometric distance, assuming we really understand this maser situation, but it's an exceptionally good case. And we find then it's been measured then that this galaxy has a distance of 7.576 megaparsecs, and it's considered to be known to about just of the order of 1 or 2%. So going forth on this talk today, I'm actually going to be using this as my calibration, my 0-point calibration. Now this isn't on the long term fully satisfactory. On the long term, we're really going to want to base everything on Gaia parallaxes. But for the moment then, and following what Wendy Friedman and Adam Rees has been doing, we'll assume this distance to this galaxy as the absolute calibration 0 point for what I'll be talking about coming up. So this particular galaxy is wonderful. It's pretty close by. Here it has this very good distance, and it's been, I'm showing you here on the bottom left the present Cepheid situation. It's very well established. The Cepheid stars are those green stars in that upper central panel. And over here on the bottom right is what you see with the tip of the red giant branch. And again, the tip of the red giant branch. I can't control this guy very well, but it is well established. Anyway, so for the moment, I'm not going to be worrying about the geometric calibration of the tip of the red giant branch. I'm just going to jump right in and calibrate it with NGC 4258, and it's kind of a nice Rosetta Stone between methodologies, because the Cepheids are there, the tip of the red giant branch is there. And so we'll be going on from that. And that will allow us to transfer the tip of the red giant branch measurements for that galaxy over to surface brightness fluctuations in a way that I'll now show. So with JWST, we observed in cycle 2 galaxies in the Virgo cluster and the Fornax cluster. Here's the Fornax cluster, 3 cases. And again, you can see top to bottom these 3 galaxies and the tip of the red giant branch measurements and the distances that we are finding for these galaxies. And I just want to show you here, this is one of those galaxies, NGC 1380, and I want to show, if I walk over here, and this, if I'm looking at the tip here, this is a plus and minus. This is, these intervals here are 10% in distance. That's a 10% distance. And you can see by eye, just by looking at it by eye, a distance of order 5%. You can see that by eye. You don't have to do anything fancy, nothing fancy. Of course, we do reasonably sophisticated analysis to get that distance, but by eye you can see basically a good distance. So here, for example, on the right is the fit of the tip of the red giant branch for NGC 4258, our calibration based on the maser, and they're transferring across to get the specific case of NGC 1380. In the Virgo cluster, we have all of these other galaxies here that we've looked at, and there's distances that we assign to it. And overall, we find a distance then to the Virgo cluster of about 16 megaparsecs. That's a little bit closer than you'll find in the literature. And that's an interesting thing in itself. And again, I'm looking at 2 different galaxies in the Virgo cluster here. I look at them here, 2 different galaxies in the Virgo cluster, and you can see by eye on that fit going across that this one here is closer than this one here. You see the tip rises a little bit higher. 16.3 megaparsecs versus 16.9, a difference of 3.6%. What I'm trying to get across here is that this tip of the red giant branch method is excellent. It's as good a way of getting distances as we have in the ways that we can get distances, and we think, and this is all with James Webb Telescope. Now, unfortunately, there is a distance, a dependence on metallicity, as we see here. Let's see, my little guy, well, I'll walk it over. So here's the tip at various metallicities, and you can see that at low metallicities, the tip is reasonably constant across all the different metallicities, but as you go to higher metallicities, it falls off, and you can see that up in this color magnitude diagram here, that if you have higher metallicities, they start to fall off. So we have to be, either we have to take that into account, or we have to be very careful that we're only looking at low metallicity stars when we make the measurement. And so we are working hard to validate this break here, and in fact we find that the difference between theoretical expectations and the observed is quite modest, and there's a break point then, such that if we only look at colors that are 1.64 or bluer, then we have about a flat. Essentially, the tip of the red giant branch is a constant with metallicity. So, with these observations with James Webb Telescope, it's very convenient that the NIRCam has these two different panels, and so we can set one panel on the center of a bright elliptical galaxy, say in the Virgo cluster, or in this case NGC 1380 in the Fornax cluster, and here's the center of the galaxy here, and we can measure that at high surface brightnesses, the fluctuations that are occurring in the red giant branch stars that are dominant there, we can measure surface brightness fluctuations. And over here, in this other panel, is we're looking out in the halo of the same galaxy. So it's the same distance, and then we're measuring the tip of the red giant branch from the stars that you find in the halo. So looking in the core for surface brightness fluctuations, looking in the halo for tip of the red giant branch. So here's the power spectrum for the surface brightness fluctuations, and it's, in this particular case, this is a nearby galaxy, and the observations are quite deep because we want to get exposures that are good for tip of the red giant branch. So this power spectrum is very, very strong, and so we now have surface brightness fluctuations calibrated by tip of the red giant branch, calibrated by NGC 4258. So that takes us up here, a strictly population 2 ladder now that's calibrating surface brightness fluctuations. And we're going to want to then use surface brightness fluctuations to go to high redshifts where we can measure the Hubble constant. Now, with Hubble Space Telescope in the past, these surface brightness fluctuations have been used in various papers going over a couple of decades, looking at galaxies in the Virgo and Fornax cluster, and indeed find this this parameter on that scales on the left, that's a measure of the fluctuations, and there is a metallicity dependence, a color dependence, which is mapped across the horizontal axis. And you can see that in the case of the two Fornax and Virgo clusters, these parallel curves here, and then if you match them, you can then get a very good distance to, or relative distance to Fornax and Virgo, which is given there. And so here we have then our current best distances to Virgo and Fornax. It's at about 16 and 19 megaparsecs. And here then is a recalibration of work that was done earlier with Hubble Space Telescope, surface brightness fluctuations, but now using the NGC 4258 calibration. And you can see here then that what we're finding, and this is preliminary, but we were finding about a Hubble constant of 74. So now what I want to show you then is some work we've been doing on surface brightness fluctuations using Hubble Space Telescope, but use Hubble Space Telescope information, in other words, surface brightness fluctuations from Hubble Space Telescope, and but with the calibration that we're now finding with JWST and going through the tip of the red giant branch that I was just showing you. Here then, in red and blue in this plot here, are data from Virgo and Fornax using the distances that I was just showing you in the previous slides. So this M bar is a measure of the fluctuations in the surface brightness fluctuations, and this is showing you their subtle color dependencies. And you can see then that this fit up here. Now here is preliminary data then with well, we have 150 galaxies. I think there's 115 galaxies in this sample here, 115 galaxies with velocities greater than 4,000, so that the peculiar velocities are not going to be a major effect on this plot. And this is showing you how they lie if you assume Hubble constant of 100. Okay, so we measure the fluctuations, and then that translates to an absolute fluctuation by assuming a Hubble constant of 100 in their velocities, and you get this plot right here. And here is shifting that to the calibration that we were just showing you. And that fit is with a Hubble constant of 74.8. Here is what it would look like shifting them to a Hubble constant of 67, keeping, of course, the calibrators the same because they have measured distances. So this is how those calibrators would look to that data if the Hubble constant was 67. The issue then arises, what's going on with all that scatter though? Because we don't see very much scatter in the Virgo and the Fornax samples. And what we can find then is probably that scatter is due to peculiar velocities. If I look on here, for example, up in what I've shown you here, I've shown you the calibrators up at the top, if this thing works. Well, I'm not getting this. Oh, well. If I look up here at the Perseus cluster, the Perseus cluster is illuminated with purple or whatever that color is there. And you see that there's not much scatter there. And that's the same thing here. If I go over to the Abell 262, here's an interesting case here of a particular nest. That's a funny name there, but the three galaxies that we have in that particular cluster, you see all three are offset about the same amount from that line there, and that would suggest that is due to peculiar velocities. Now that would be a very large peculiar velocity of about 700 kilometers per second, but the overall scatter here is about 300 kilometers per second. So it's a plausible thing. And then once in a while you see, here's a case of one case with bad data. Look at the case here of the Hydra cluster. 3 cases that are in very good agreement, but there's one funny one over here. Looks like bad data. So anyways, so there's the occasional bad data, but it looks like the scatter there is arising from peculiar velocities. In particular, if I look here so what we did is we had a snapshot Hubble Space Telescope program, and in many groups we have more than one observation. So that in these cases the two galaxies have to be at the same distance, and we can then look at the scatter in our M-bar measurement of the surface brightness fluctuation. Oops, what did I do? Oh, I went with that. And here's the distance modulus distance pairwise. So we had 62 pairs of galaxies in mutual groups, and we can see then that the overall scatter is 4.7% in distance in these pairwise scatters. So that's giving us how good the measurements can be. So upcoming, though, in the current cycle coming up, cycle 4, we'll be getting then more measurements. So we'll be adding, and we'll be approximately doubling the number of calibrator galaxies, and we'll also be increasing. Okay, that's the next conversation. We'll also be increasing then from available observations with our SNAP programs. We'll have about 250 Hubble Space Telescope surface brightness fluctuation measurements going out to about 100 megaparsec. But maybe 100 megaparsecs isn't far enough to measure the Hubble constant. There still can be peculiar velocities affecting that measurement. So in the current cycle 3, we are measuring galaxies in the Coma cluster, and all our data has just come in the last few weeks. So we have actually 38 fields, 38 primary galaxies in the Virgo cluster, and with secondary galaxies in the fields, we'll have about 100 galaxies in the Coma cluster with surface brightness fluctuations, which will allow us then to, in the JWST bands, get the equivalent to this kind of a calibration here of the surface brightness fluctuations as a function of their color. So at the end, coming in the next few months, we will have a JWST calibration, which is really very strong, and a distance to the Coma cluster, given our absolute calibration in Virgo and Fornax, we will have an excellent couple of % measurements of the distance to the Coma cluster. And here's just examples of how those fields were laid out. So here's just this is again going back to the measurements then of the surface brightness fluctuations with Hubble Space Telescope. And so what I'm just comparing here is the distance modulus from the HST surface brightness fluctuations, and I'm just comparing it with distance modulus for the same groups in the cosmic flows for collection of distances. And you can see that the fit is very good. In other words, what I'm showing here is that there's good consistency between the HST surface brightness fluctuations and distances in the cosmic flows for catalog. And just showing you up there the Hubble constants that are for those two different compilation. So in other words, the cosmic flows 4 is a good consistent database. Well, that's about all I wanted to say today. The other thing, of course, that we're doing here is mapping out peculiar velocities and the distribution of galaxies, the distribution of masses with cosmic flows 4, and I just show you that there's some validation from surface brightness fluctuations, and so that's what I've got to tell you today. So thank you.
Questions?
Thank you for your talk. I am very interested in knowing on your values for the TRGB distances for Virgo and Coma and everything. Your distances with your TRGB approach do look more like the ones obtained by the Adam Rees, the Hughes program, or the ones obtained by the Carnegie Chicago program by Wendy Friedman and Taylor Howitt, because it's really very different. You get for some galaxies difference of 0.08 in modulus of this in magnitudes in modulus. It's really huge, the difference between the distances obtained by one group and the other. So I wonder, your group is more obtaining like something more like Adam Rees, or?
They're not focusing on those two groups. They have some individual measurements in Virgo and Fornax, but they don't particularly focus on those. So I don't think there's enough data to make a comparison there. The only comparisons I think we'll ultimately make will be on large scales. For example, the Coma cluster will be a great place because there are a lot of other measurements that are in the Coma cluster. That'll be good. I think it's, in the fullness of time, we'll be looking at these cross correlations with them. But for the moment, I think the virtue of what we're doing is that it's independent. It's totally independent, and in the fullness of time, we'll look to see how they compare.
Thank you very much.
Hi, thank you for the great talk. I actually have two questions. The first one is, could the source of scatter be also due to intercluster dust or something like this? Or have you looked into the possibilities of having more astrophysical effects instead of peculiar velocities?
Well, intracluster You know, first of all, we're working in the infrared. That sure helps. And the tip of the red giant branch, we're looking out in the halos of galaxies. Again, that helps. So with surface brightness fluctuations, there can be dust in the centers, and that affects the surface brightness fluctuation measurements. We, of course, are trying to, in our images, if we see dust, we kind of mask those out. Yeah, so I don't think dust is a big issue, but of course it could sneak in some issues.
Okay, thank you. The other question, if I may, is so I'm not so familiar with it, but would it be possible to use, because you have a unique galaxy as a 0-point calibration, would it be possible to have more galaxies in order to make this 0-point calibration to avoid having such a dependency in this unique galaxy?
Of course. This is unsatisfactory right now to just have 4258. As I say, a virtue of it is that Adam Rees and Wendy Friedman have been actually using just that one for recent papers. And so it's an interesting comparison because, of course, there's been disagreements. Of course, in the fullness of time, we're going to want to use Gaia parallaxes to give us, going through our Lyrae stars probably, to give us then the calibration of the TRGB. So that's going to be Gaia, our Lyrae, TRGB, and that'll be much more robust.
Thank you for the nice talk. So what's the prediction for your uncertainties? Can you be more precise than Adam Rees?
This shows you what we've been doing then with coming up. So I was just telling you about the coma cluster in cycle 3, which will be very good. In cycle 4, we'll be improving the linkages between TRGB and SBF. But the other thing is that we will then now with JWST, we have a survey that will be going out to about 300 megaparsecs. It's like it's a new mode that they have with JWST, where we give them a big sample of galaxies, of 300 galaxies, and say, just observe whatever you can of those. And so the final result's going to be dependent on how many galaxies we get out there. But if we can get, not necessarily just in the single cycle, but in the future, if we can get about 100 or so, we'll be able to drive down uncertainties down at the 1% level. Now, again, we got to have the 0-point calibration through the Gaia and our Lyrae stars to TRGB. Again, there's 1% possibilities there too. So then the final thing is, though, what are we actually going to find when we look out to 300 megaparsec and we look in this direction and we look in that direction? The nice thing about JWST is same telescope, same filters, so there's a lot of possible systematics that you have with supernova that are not there with this. But what if there's peculiar velocity flows at that level? That'll be exciting to know. But let's say we have a nice calm universe that's just expanding isotropically at that level, 1%.
Any last question? I'll ask a very quick one. For cepheids, one worries a lot about crowded field photometry. Do you have any issues as far as the surface brightness fluctuations with crowded fields?
You know, again, it's better than with cepheids, because cepheids, you're looking at the inner parts of galaxies where there's dust. We're tip of the red giant branch. Of course, we're looking out in the halos where there is not such issues. With surface brightness fluctuations, if you like, it's a global. You know, we're not trying to resolve out the only issue there. The issue there is well, globular clusters and dust. Okay, so those are issues that we have to confront.
Good. Let's thank Professor Tully again.